And since moles of solute over kilograms of solvent is molality, we can simply write a small letter M for that. But we need to say that it's the NaBr or NaBr solution. Okay, so that's our molality. Now that's just one starting place because now we have just this term. Okay, so we can start plugging in numbers for these terms. All right? No, we're just done with the molality right now. All right, the second part is to plug in the terms we have here. So the delta T for freezing is equal to I. I is the number of particles a substance breaks into when you dissolve it.
You might take the problem off and move it up.
Okay. Well, when we built this formula for sodium bromide, we can see that it was made of two particles. 1, 2. What?
Is that what we look at?
That's an easy way to find it. Okay? If you build a formula using the system we've taught in this class, then it's pretty much right there. Okay, really you break it apart, but breaking it apart is just undoing this. Now that's assuming it's a soluble salt, and only soluble salts dissolve. You figure that out whether it's a soluble salt by looking at the solubility rules.
Could you count them, like, when you do the molar mass, like, could you count the Na and there's 1, 2, 3?
Say again?
Could you not, like, when you do the molar mass song, could you count them?
No, because sometimes you have polyatomic ions. Polyatomic ions don't break up, but you do have to break up the individual atoms in the atom inventory. Does that make sense?
Yeah.
Okay. So polyatomic ions don't break up in solution. So you don't count the number of atoms in a polyatomic ion to get the I. You only count the number of polyatomic ions. Okay? All right. So we have 2 here for the I. Van't Hoff factor is the number of particles that the formula unit breaks up into. All right. The K sub F part of this we get from your references. Okay, you have one of these on page 340 of your handout. You need to get that out if you don't have it out. You need to practice with tables that look like this. We're looking for the K sub F, and we're looking for the K sub F that applies to the solvent. The solvent in this case is water. Okay, so where these two intersect here, there's the number we're looking for. And since we never put units of measurement in the cells where the numbers are, we look in the column label for the units to go with it. Okay, so it's negative 1.86 degrees C per mole. Okay, then we want the molality for the last term, the M term here. And the molality we calculated at 0.8378 mole. Now just to make everything work out nice and neat to see what's going on for dimensional analysis purposes, we can put any numbers that aren't already over 1, cancel out the units that can be canceled out, so those concentration units can be canceled out, and do the math. And we get, say again?
How do you get I?
I is the number of particles that a formula unit breaks up into when you put it in solution. And since this is a soluble salt, it's going to break up into the 2 particles we used to build it. Okay?
So it's just how many?
Particles it breaks up into. And only soluble salts break up. Anything else, if it's not a salt, if it's not an ionic compound, it's not going to break up. And so you just, I is 1 in that case. Okay? All right. So let's do the math here. So 2 times negative 1.86 times 0.8378. Okay, and we get a negative 3.116616. The units we have left are degrees C. We need to look at the numbers and figure out which measured or calculated numbers have the least digits. Which one of the measured or calculated numbers is the least precise. This is not a measured or calculated number. This is a counted number. We counted the number of ions. 1, 2. So we don't use this one. We do use this one. This one was calculated. This one was actually calculated as well. And this one has the least digits, only 3 digits. So our final answer needs to have 3 digits. Starting with this number, 1, 2, 3 digits, we underline from there over and round it off to negative 3.12 degrees C. Okay, that's our change in temperature. It's not the temperature we're looking for. It is how much the temperature is going to change. Okay, so that's what we plug into this equation. Okay, so this equation, is delta T equals temperature final. That's what we're actually looking for, temperature final, minus temperature initial. All right, delta T we just calculated. This is the delta T we just calculated. So it can plug in negative 3.12 degrees C for that delta T. T sub F we're looking for. We don't have that yet. And we're going to subtract T sub I. T sub I is always the temperature at which the pure solvent either freezes or boils, depending on which one of these you're looking for. Okay? So what we want to know is what temperature does pure water, at which temperature does pure water freeze? And that's 0.00 degrees C. Now, if you didn't know that, it's right here on the table. Normal freezing point for water, 0.00 degrees C. 0.00 degrees C. I mean, you probably should know that, but just in case you didn't. And what we need to do is the same thing we did in the last unit, where we did isolate the unknown. We're at that point in the problem we need to isolate that T sub F. We do that by, in this case, since we have a subtraction problem here, we need to add something that will get rid of this term. So we're going to add 0.00 degrees C to this side of the equation. But if we do it to this side, we also have to do it over here. So plus 0.00 degrees C. Since I added a negative one of these to a positive one of these, all I have left is T sub F. Those basically go away. Okay? And when I add this number to 0, I just get the number I started with, 3 T sub F. Temperature final. T sub F is temperature final. And so our final temperature, freezing temperature, for this particular solution is a negative 3.12 degrees C.